All right, let's spend some time talking about differentiability, which is really answering the question, does the derivative exist? And usually we're interested whether the derivative exists at a point or not. And so there really are two requirements. The first requirement is that the function has to be continuous at the point we're interested in. And the second requirement is that the left slope equals the right slope. Again, at that point in question. So I guess we can define those in terms of a little formally. Remember from a previous talk, we had for something to be continuous, the limit of the function as x approaches a has to equal f of a. This is what it means to be continuous. So we're coming from the left side, we're coming from the right side, and we're going to the same point, and the function's actually defined at that point, and it agrees with that, meaning the y values are the same. Okay, for the left slope to equal the right slope, we're talking about the limit of the derivative, so the limit of f prime of x, and if you haven't seen that notation yet, f prime is just one of the ways to talk about the derivative, as x approaches a from the left, would have to equal the derivative as x approaches a from the right. If you put both of these things together, really what those mean, and I think this is the best, locally linear. Okay, because if you're interested in a point and you zoom in, and it doesn't matter what it is, take any random function, and I'm interested in the derivative at this point right here, let's say, and I zoom in there, it's going to look linear. Well, why? Well, because at that particular point it's continuous, because if I approach from the left and I approach from the right, I'm meeting at the same y value, and the function's value at that is the same as the limit, and the slopes agree. So if we look at the slope just before and the slope just after, they're that same slope. Now the slope changes, but it doesn't matter what point I zoom in. If I zoom in right there and I blow that up, so take that box and blow it up bigger, it's still going to look linear. And to look linear, you have to meet both of those requirements. Sometimes it's easier to talk about, well, if that's what it means to be differentiable, meaning the derivative exists at those points, how could it not be differentiable? So let's come over here and then look at problems. So what are the problems? And I will give you the names, the graphs, and then a corresponding function. So what if we had a graph that looked like this? Okay. What if we have an absolute value graph? So we're talking about the square root of x. And we'd end up calling this an example of a corner. It doesn't matter how much you zoom in, this particular function is not differentiable at 0. It's got a limit, it's continuous, but it is not differentiable because there's no way the left slope ever equals the right slope. If you zoom in there, it's always going to look like that v. Okay, another example of a corner would just be some piecewise defined function. We could have a piecewise defined function which has, let's say, a slope of 1, and all of a sudden it changes to a slope of like a half. Okay, no matter how much you zoom in there, it's always going to have that bend in it. Okay, so that's an example of a corner. Let's look at a cusp. So an example of a cusp would look something like that. Okay, this is what they call a cusp. Okay, and if you look at it, it's actually approaching an infinite slope here and a negative infinite slope on this other side. An easy example of this is y equals x to the 2/3. That's an example of a cusp, and again, it's differentiable everywhere on its domain. Everywhere over here it's fine, it's just not differentiable at 0. Okay, let's look at a vertical tangent. So this would look something like this. An example would be y equals x to the 1/3, right? This is what they call a vertical tangent. If you look at the slope at x equals 0, it's going to be an infinitely big slope. I didn't really draw it. It doesn't look big enough, but really the graph would go straight down right there at 0 and be infinitely big, and that's a problem. And then what else? Well, again, all of these corners, cusps, and vertical tangents violate this restriction. But remember, if it's not continuous, it's also not going to be differentiable. So any of our old continuity issues, any continuity problem will then also cause a differentiability problem. So we have to look at our hole. We could have a hole. Again, the left slope and the right slope agree, but if it's not continuous, it's not differentiable. We could have a jump. And again, we could even lead off with the exact same slope. The slopes could be the same here and here, but if it's not continuous, it's not differentiable. And of course, we could have some vertical asymptote. We could do this. And again, any continuity issue is going to be by default a differentiability problem. Okay, let's do one kind of algebra example. We'll look at one, this is probably the favorite of some teachers and certainly the AP. So I'm going to give you some function, f of x, and it's going to be some piecewise function. So let's make it ax plus b, and we'll make that valid when x is less than 2. And then we'll have another function be 4x plus 3, and we'll define f of x then if x is greater than or equal to 2. Okay, so what do we need to do? Well, we need to make sure we want to find a and b, so that's our goal, choose a and b to make it differentiable. You're like, oh man, how do I make this differentiable? Well, you have to follow the two restrictions. We have to make the y values the same, and then we have to worry about the slope. Okay, the y values and the slopes. And again, this is just some quadratic, and this is just some line. We don't have to worry about the quadratic and line anywhere on its domain. As we're at 3, 4, 5, it's going to be differentiable, and this is going to be differentiable. We just have to worry about this breaking point. This is some piecewise defined function where it goes from a parabola to a line. We have to make sure that a and b make these things happen. So let's focus just at x equals 2. So remember, if x equals to 2, that's our whole goal here. And so if we look at x equals to 2 for a y value, that would make the top function 4a plus b, and it would make the bottom function 11. Okay, so if this is true, then we know that our y values here and here will be the same, which means it'll be continuous. And now we need to look at the slope. Again, I'm going to look at the derivative, and if you don't know how to take a derivative yet, then you might have to go back and look at that section. But the derivative of ax squared is 2ax, and the derivative of b is a constant, it's 0, and the derivative here is 4. But remember, we're looking if x is equal to 2. So when x is 2, this is just 4a needs to equal to 4. And again, the red is guaranteeing that the slopes are the same. The blue is guaranteeing that the y values are the same. Okay, so this tells us that a has to be 1. But if a is equal to 1, then this is just 4b plus, or 4 plus b equals 11. So then b has to be 7. And so what we've decided here is that this function has to be 1x squared plus 7 and 4x plus 3. And if you look at that, it will give you y values equal to 11. So see how they're both equal to 11 when x equals to 2, and then they both have slopes of 4. And what that means is if you draw the graph, remember, we're going to be a parabola, x squared plus 7. So here's x squared plus 7. And then at 2, we're going to stop. And we're going to be an open circle. And again, this is the point. When x is 2, this is the point 2, 11. That's this point here. And then you start working with this function to the right. Remember, it's this function when x is greater than or equal to 2. But what is this function when x is 2? It's 11. And what slope does it have? A slope of 4. So it goes off with the slope of 4. And if you zoom in right here, it's going to be locally linear. They have the same y value and they have the same slope. Remember, they both are going to have the slope of 4, and they're going to meet at that point 2, 11. So then I successfully found a and b that made this function differentiable at 2, and we already know it's differentiable everywhere else.